In some situations, we look at the population variability. For instance, in manufacturing, uniformity drives production's quality. Even in sports, a soccer player is interested in the ability of a player to score in a uniform way rather than making goals in one game and not scoring for a number of games. So the variability of the player's performance is important. We look at the chi-square distribution, which is used to test variance in the one sample situation. Assumptions for testing variance basically are the normality of the population. So we are looking at a population with a given mean mu and the standard deviation sigma, which is normally distributed. The inferences about variance, so about population variance sigma squared, are made by using sample variance S squared as an estimator. And we look at the sampling distribution of the sample variance S squared and introduce the chi-squared distribution, which depends from n-1 degrees of freedom and is stated as the sum of the squared deviations xi minus x bar squared. So this is basically the same thing as sample variance multiplied by n-1 divided by the population variance sigma squared. So we generally use this one as the formula for chi-squared distribution. This distribution is right-skewed and depends, as already said, from n-1 degrees of freedom. So again, it's a family of curves. And the chi-squared variable, very important, cannot be negative. So the tables are built on the right. So they give us the chi-squared value at alpha and then -1 degrees of freedom. So for left-skewed test, because the tables are done to the right, we will have to go at 1 minus alpha so that we are looking at the left tailed value. We'll see this one better. So let's show you the use of the tables, and let's assume alpha is 5% and n is 12. Therefore, the degrees of freedom n-1 will be 19. So let's do the three situations. So for a right tail test at 5%, the rejection region will be the 5% on the right. Therefore, we simply look at the tables at 5% and 19 degrees of freedom, and we'll find the value of 30.144. Now imagine still at 5% and then degrees of freedom, we have a left tail test. So the tables are done on the right. So we need to calculate how much is this part. And because this part here is alpha, this part is going to be 1 minus alpha. And so 1 minus 5% is going to be 95%. And so we'll have to look under the 95% column, or 0.95 and 19. And this column is symmetrical in the tables, appears symmetrical to the other column. So the 95 is the fourth column from the left, and the 0.05 is the fourth column from the right. So we look symmetrically, and we find a critical value of 10.117. And finally, if we have a two-tailed test at 5%, so for the right rejection region, we need to divide alpha in 2 and find 0.025. And then we need to look at 0.025 and 19. And the value that appears on the tables is 32.852. For the left tail, we'll have to look at this quantity, and this quantity is going to be 1 minus alpha by 2, which is 0.975. And so we'll have to look under 0.975, which is symmetrical to the left, to the column of 0.025, and 19 degrees of freedom. And this time, the value that we find is, of course, smaller, and it's 8.907. And so here is the recipe for the test for variance. The null hypothesis, like in all one-tailed tests, is in terms of variance, in terms of population variance. And so the population variance sigma squared is going to be assumed to be equal to a given value, sort of an hypothesized population variance, which we'll call sigma 0 squared. Alternative hypothesis is, as usual, a choice of 3. So the two-tailed hypothesis is sigma squared different from sigma 0 squared, or the hypothesized population variance that is generally given in the test. If we have a left-tailed test, then we'll try to prove that sigma squared is less than this value. If the wording is right-tailed, then we'll have to try to prove that sigma squared is greater than sigma 0 squared. So this is the claim. This is the alternative hypothesis is what we wish to prove. We always assume that the null hypothesis is true, and therefore our conclusion will still be in terms of null hypothesis. Special word in case the test is talking about standard deviation. We can use the test for variance for standard deviation, but because in the formula we have variances, we prefer to express the hypothesis in terms of variance. So if it's asking you that the standard deviation is, for instance, above 2, then we'll word it in terms of alternative hypothesis that the variance is greater than 2 squared or 4. So make sure to make the conversion, and then when you conclude, revert back to standard deviation. And the formula for the test statistic is from the chi-square distribution, and it's n-1 sample variance divided hypothesized population variance, and the degrees of freedom are n-1. We already showed you how to use the tables for two-tailed, left-tailed, and right-tailed. And just a reminder that to calculate sample variance, if it's not given to you, use the usual formula. I have the computing formula down, this particular one, sum of data squared minus fraction, sum of data and then squared at the top, divided by n at the bottom, and everything divided by n-1. We'll follow up with some examples. Thanks for listening.